In lesson 5a, we're going to look at polynomial functions and their complex zeros. So we all know about real zeros, right? And those are going to be x-intercepts, right? So we know about these being our real zeros, right? It could be like -4 and +2, and we come up with a polynomial with those using those real zeros. But polynomials also can have imaginary zeros. So if you do not have x-intercepts, this will still have two zeros, and they're going to be complex because they do not go through the x-axis. Right? So we have already looked at some of the real, and now we're just going to add in some of the imaginary and complex. So just a reminder that when we're working with this, we learned in Algebra 2 how to take square roots of negative numbers, right? By breaking them up into a positive part and -1, right? Basically rewrite the negative sign as a -1, right? And take the square root of both of them. And we learned that when you take the square root of -1, you get this imaginary number called I. So the square root of 9 is 3. The square root of -9 is 3i. Right? And that's to be considered a imaginary number. Now, imaginary number can also be complex, right? So that's when it has a regular number, which we call A, and then its imaginary part, B, followed by the I, so we know that that is the imaginary part. So we can have, and A is the real part, and B is the imaginary part. We always have the I following the B to know that it is the imaginary part. So all imaginary numbers are also complex numbers, right? If you just imagine the A is equal to 0, that would be the same as an imaginary number by itself. So we could rewrite like 3i as 0 plus 3i, and that was called complex form. Okay? And this is just review from Algebra 2. Okay? You don't necessarily need to know every little thing about it, but it's good to brush up on these properties before we move forward. Alright, so one of the biggest theorems in algebra is actually called the fundamental theorem of algebra, right? And this is the definition of what it means. However, basic thing is that if you have a polynomial, let's say it's x squared, you have this many roots no matter what, right? So whether it's going to be like this, 2 real roots, right? Or it's like this with no x-intercepts, that means you have 2 imaginary roots. But in any case, or if you go like this and it actually hits it one time, that's 1 root but with multiplicity 2. But in every single case, that has 2 roots, that has 2 roots, and that has 2 roots, because that is the highest degree of the polynomial. So if that was a 3, there'd definitely be 3, right? And you can have a combination of real, complex, or imaginary, and of course you can have different types of multiplicity. In any case, all of them will always add up to 2. All the different types of roots will add up to however big your degree is here. Alright, so what we're going to do is factor a little bit and try to find out what those roots are from factoring. Right? So we're going to go back to Algebra 1 and pull out some old skills. So first thing you may notice is that these all have a x variable as a factor. So you want to factor out just that GCF is what we call it. So we'd be left with x squared if I took it out from here. If I took an x out from here, I'd have minus 6x. Everything's basically going down by 1 degree of x. Alright. And I already know I have 3 roots, right? So my end goal, if you want to think about it, is to have this. I'm going to have my GCF I factored out, and then 2 more factors, and altogether this will make 1, 2, 3 roots, because of the fundamental theorem of algebra says I must have that many zeros. Complex or real, whatever types they are, they have to be 3 of them. Okay. So take a moment. You might try to factor this and say, what 2 numbers multiply to 13 and add to -6? However, that's a prime number, and multiplying to 13 doesn't really help us get to -6. So in that case, we will have to go to the quadratic formula. Right? So you'll have to know all these different skills as needed, as you're just doing any math problem Right, so we'll have b squared, which is 36, minus 4 times a, which is 1, of course, times c, which is 13, all over 2 times a, which is just going to be 2. All right, so we'll simplify this. Everything inside here, which is called the discriminant, is going to equal negative, looks like 16. So you can already see that we'll get an imaginary answer here because we have a square root of a negative. All right, divided by 2. And as you saw above, the square root of negative 9 was 3i, so the square root of negative 16, right, comes out to be 4i. Notice we get that plus or minus divided by 2. And then we can simplify a little bit here. These each have a factor of 2, so I'm going to rewrite this as 2 goes into 6 3 times, and 2 goes into 4 2 times. So those are my two complex roots, along with this other root up here, right? That makes 3. So I can rewrite it in this format now. So we'll have x minus, my first root, I'll do the positive one. So x minus 3 plus 2i. Close that. And then I'll have my second, which is going to be x minus 3 minus 2i. Right? So these are identical except one's plus and one's minus because of this, the plus and minus 2i. Right? So that would be the factored form, and we can even distribute this negative, make it a little bit cleaner. So I'll have x minus 3 minus 2i and x minus 3 plus 2i. Alright, so that is a fully factored form of that polynomial. And know that this is all reversible, that if we wanted to put this in a matrix and multiply it all back together, we could do this whole process in reverse and it would bring us back to this answer. That is the fully factored form right there. Okay, so let's try another. Number 2. Right, look for your GCF just like we did on the last one. Notice how they both have a y, so we can factor that out. Left with a 4x and a squared and plus 25. And once again, you might look at that and try to factor. You see 4 and 25, you might be thinking difference of squares, but this is a sum, so we can't really use that. Right? So what we can do, though, is that we can just go off and solve this by itself. Right? So we can say 4x plus 25. Right? Set that equal to 0. So we have 4x squared. I'm going to subtract 25 on both sides. So minus 25. I'm going to divide both sides by 4. So I'll have x squared equals negative 25 over 4. And lastly, here, let me take the square root. Right? So I'm going to do x is now going to be the plus or minus square root of negative 25 over the square root of 4. So on top we get the 5i. On the bottom we get 2. And we don't really need to worry about, like here, taking the square root of 4 and saying plus or minus 2 because we already have the plus or minus in place. Alright, so we do have three different factors here. We got the y that we took out at the beginning. And we have a x plus 5 over 2i and x minus 5 over 2i. Notice how we usually write the I after the factor as opposed to having it on the numerator here. We usually write it after. but they are equivalent statements. All right, so let's go further on and review the even and odd multiplicity. Right? So if a polynomial has a factor that is repeated, these duplicate roots are known as multiplicity, as in multiple roots. And you can have many degrees, say, of n. So depending on how many roots there are, you could have a multiplicity of 1, 2, 3. It can go up to many. Okay. So the general rule is if f has a real zero of odd multiplicity, right, 1, 3, 5, and so on, right, then the graph of f will cross the x-axis at whatever that number is, comma 0, right on the x-axis, right? So cross or go through. So let's say if odd multiplicity would be like x to the 1 power, so like 2x plus 3, right? It crosses the x-axis. It goes through the x-axis. That's all they're saying. Crosses just means goes right through. And that the root would be at whatever number that is, comma 0, right? Because anything on this axis is going to have a y-coordinate of 0. Right? Whereas if f has a real zero of even multiplicity, then the graph of the f will be tangent, is the mathematical term, or I like to say bounce, off the x-axis at that location. And best known example of this is if we have an x to the second, right? So we have an even, and we all know when you graph that, it goes down here and it bounces right off of the axis, right? So technically, yes, this is tangent, right? Because it touches at one point. Tangent just means it touches one time, right? Which, of course, is a bounce, right? If it, like a ball bouncing on the ground, it hits it one time, it bounces right back up. So that is what the multiplicity means. So x to the second power has 2 roots, but the multiplicity is 2. And that's how we get 2 answers, even though it appears to only touch the x-axis at one point where it's tangent. There's technically a multiplicity of 2, thereby giving us 2 solutions, according to that fundamental theorem of algebra. Okay, let's keep going and look at these zeros of odd and even. I'm going to graph. So if you use a graphing calculator and you sketch this, right, you'll notice that you have an odd multiplicity right here. And before I use example of just going a straight line, but this is odd, and you notice it still goes through, right? It goes right through. But it kind of goes increasing, goes to 0, and increases again. So when it goes increasing to increasing, or decreasing to decreasing, you often get a multiplicity of 3. That's what it means. Okay? And then we also have our other root here that has a multiplicity of 2, right? So it's tangent right here. Oh, sorry, multiplicity of 2 at positive 1. So it is tangent. It bounces off. So while this might appear to have only 2 x-intercepts, right, it's definitely not like a quadratic. It's not an x squared type of polynomial. It actually goes up to the 5th degree, right? 3 multiplicity here for negative 2, and a 2 multiplicity for positive 1, thereby making a 5th degree polynomial. Okay. And it says, okay, we should probably write all that out. So let's see here. We got this, x plus 3, x plus 2 to the 3rd power, right? That's going to be odd, right? And the root will be at negative 2. And then we have x minus 1, which is going to be an even multiplicity at 1, x equals 1. And we can say this has a multiplicity abbreviate multiplicity of 3, and this has a multiplicity of 2. So crosses here at the odd, it bounces or tangent at the even. Odd, crosses through, bounces, even. All right, below is the graph of the polynomial h of x. Based on the graph, what is the smallest possible degree of h of x? Use your knowledge of zeros and other graphical behavior to justify your answer. All right, so we know about multiplicity, and we also know about turns. So we can look at this several different ways. So we have 1 turn, 2 turns, and 3 turns. You might recall that the degree minus 1 equals the number of turns. So if the number of turns is 3, it makes sense that this is going to be a 4th degree polynomial. Now we can also look at it from what we just saw, that it crosses here, so that's going to be 1 root. It crosses here, that's going to be 2 roots. And it bounces here, right? So we know that's going to be 2 roots, multiplicity of 2 for the bounce. So together we have 1, 2, and another 1 right here, right? So we have 4 total roots that we can count up, also making it a 4th degree polynomial. So either way we look at it, number of turns or the types of roots, we come up with an answer of 4th degree polynomial. Right? And you can explain that in your own words. Right? There's not a right way to say that, just include all the information. You can use the explanation with the turns, or you can use the explanation with the roots, either way. Okay, let's go over here. It says, below is the graph of the polynomial function k of x. Use the graph to create a possible equation for k of x. So knowing that we have, right here, we have a root of -2, but it is multiplicity of 2. And we also have a root of positive 3. Okay, so let's just list these out. So my roots, I list all of them, right? My zeros, I can call them as that as well, zeros. Also x-intercepts, those all mean the same thing, right? They are -2, and there's 2 of them, -2 and 3. So I have all 3 roots, right? So I can write this in the format like they want, k of x, and there's always some number in front. Okay, we don't know what that coefficient is, and we have to figure that out. Okay, so some coefficient in front, but I do know it's going to be x minus -2, x minus -2, which is x plus 2. Repeated one more time, x minus -2, x plus 2, and x minus 3. And I can use another point on this graph to help me figure out, well, what is this a value actually? So I'm going to use this x-intercept. I'm going to assume that this is 0, 2. And I can plug that in for x, 0, right? And for k of x, right, I can plug in 2. So for each of those x's, I'm going to plug in 0. Try to keep the same schema here. There we go. Okay, let's just switch to black. So from here, we have 0 plus 2, right? That's 2 times 2 times -3. Right, so if I simplify everything, I'll have 2. I'll have my a, and then this value over here turns out to be -12. And if I divide both sides by that -12, I have a by itself. So it looks like 2 over negative 12, which is negative 1/6, is what a equals. So my final function here will be k of x, and exactly this, right? All of this, but I now know the a is equal to this negative 1/6. So we got negative 1/6, and I'm going to do a little shortcut here. Since I have two of these, x plus 2 and x plus 2, I'm going to rewrite that as x plus 2 squared, and then just have the x minus 3 at the end. So that is the full polynomial, and if you were to check this in the graphing calculator, you'd see it matches up with the graph as well. So lots of little algebra that we're practicing here. All right, let's keep going. We have the conjugate root theorem. All right, so looking at conjugates, and we multiply these together, and we found out that they're always come in a set. So go through this. If p of x is a polynomial with rational coefficients, then the irrational roots of p of x equals 0 occur in conjugate pairs. Okay, a fancy way of what we're really saying here is that when you're solving these equations, much like we did earlier, let's find that problem we did earlier right here. You'll notice that you get two of them, right? You get a plus and a minus because of the square root. You always, when you take the square root of both sides, you always end up with a plus or minus, right? So the positive 5i over 2 and the negative 5i over 2 we call conjugates, and that occurs with imaginary numbers and with square roots in general. Okay, so that's all this is that recognizing that once we do that, we always get, if we get a plus root b as an answer, then we'll get a minus root b as an answer, because we have the plus or minus, right, version. So those are always conjugates. And we have the same thing for complex, right, for the same reason. Only difference here is that the number underneath the square root was a negative, so now it's imaginary. In this case, the number under the square root is a positive, so it stays as a regular rational number. So now we have a minus bi. Okay, so a little corollary, right, which is kind of a little extension. If a polynomial function of f, polynomial function f of and blank degree of real coefficient has at least one zero. So how can you get at least one zero no matter what? So if you think about it, if every time you graphed maybe an even, it's possible to have no real roots, right? Because if it stays away from the x-axis, right, it was always possible to have no answers at all, or no real numbers anyway. However, if it was an odd, when you had one side that goes down and one side that goes up, something like this, you can see there's no way to draw an odd function without having at least one real root, one real coefficient, right? So for all odd degrees, you're always going to have at least one, and since this would be like a third degree, the other two would be imaginary or complex. Just the observation that odds always have at least one real. All right, so let's look at example 6. A polynomial function f of degree 5, fifth degree, right, whose coefficients are real numbers, has the zeros of x equals 2, 3i, and 1 plus I. So this is just applying that we know there's 5 roots total. They gave us 3, and according to what we just set up here, if there's a positive, there's also a negative, and if there's a negative, there's also a positive. So the fact that they gave us one of the roots is positive 3y, we also know the other one is negative 3i. And same thing here, if we know one of the roots is 1 plus I, automatically we know its conjugate, 1 minus I, is also a root. So those are the remaining zeros, right? Because these always come in pairs. So we have a total of 1, 2, 3, 4, 5 roots, and that is a fifth degree polynomial. let's move down here. So we have find a polynomial function of degree 4 whose coefficients are real numbers and have zeros of 2, 2, negative 3 plus I, and assume a is 1. So what they're doing over here that we did earlier, this a value, we don't have to worry about doing it. We're just going to assume that it equals 1, so this last part is not going to be needed. So they're saving us a little bit of work here. We just have to do this part where we put the roots in here, multiply it all together, and then we'll be done. All right. So degree 4, notice how they gave us 3 again. All right, so let's write out the fourth one just to be complete here. That'd be negative 3 minus I. Okay. And notice that we do have a multiplicity here of 2. So for that part, I'm going to write x minus 2 and x minus 2. Multiplicity of 2 is just going to be to the second power. Okay. And then for the other part, the complex, I'm going to have x minus negative 3 minus I. Let's do plus I. Let's do that one first. That's this one right here. So I'm just doing x minus and then whatever the root is. And then I'll do x minus, and my other root is negative 3 minus I. Okay, and I think both of these need another parenthesis to close it. There we go. And let's simplify a little bit, distribute that negative, so x plus 3 plus I, and we'll have x plus 3 minus I. And we still have the x minus 2 in front, squared. All right. So you'll notice we have a pattern here, right? We have something plus something times the same something minus the same something. Believe it or not, that's like a difference of squares. So that's the same as doing this. If we had x, let's say, plus 2 and x minus 2, there was a shortcut called difference of squares, right? Which just meant the answer is going to be x squared minus 2 squared. So if you try to do like the multiplying, the middles cancel out. We get a negative 2x and a positive 2x, which just cancel out and equals 0. So it's really just a shortcut of multiplying it all out whenever you have that pattern. So we can do that here because we have x plus 3 plus I and x plus 3 minus I. It's the same format, it's just instead of x, it's an x plus 3. So I can rewrite this as x plus 3 squared minus I squared. And this will take a lot of the heavy multiplying out of the problem. If we multiply this manually all the way across, it would take quite some time. Could do it, but this saves us a little bit of time. All right, and we'll expand this. We're going to keep on going and see what we get. Okay. Let's see here. Let's just do, you know what? What we're going to do is we're going to leave this factored here as is, and I'm just going to rewrite this part a little bit more simple. All right, so we're going to do x plus 3 squared, right? So we are going to get x squared plus 6x and plus 9. Remember to double this number for the middle, and then you square that number for the end. And then over here we have minus I squared, right? Now you might remember I squared is the same as negative 1. So we're actually subtracting negative 1, so that's plus 1. So I'll do one more step and just simplify. X minus 2 squared and x squared plus 6x, and then these two together make 10. All right, and I'll leave that together. Now, if you really wanted to keep on going and get that full polynomial, you could multiply this out and multiply these two trinomials together, and it does work. However, we're going to save some time for ourselves. Instead, let's just go into the calculator and plug this in, put this in the graphing calculator, and see what it looks like. So I'm going to bring mine down here. Let's make it a little bit smaller. Go to y equals, and punch away. So we have x minus 2 in parentheses to the second power to the right, and then we have x to the second power plus 6x and plus 10. Right? Now, if you tried to put like the earlier version of this with the i's in there, it does not work. So you have to have a complete polynomial version with no i's or complex in here to be able to graph it. And then when we go to here, you can see part of the graph. Now, this should be suspicious because we know it is we should be suspicious of this because it looks like just 2 roots, right? That looks like a multiplicity of 2. We're expecting 4 answers, right? 4 different roots, so something's off a little bit, right? We need more turns. We need at least 3 turns if this is really a truly 4th degree polynomial. So that's a little hint. Let's zoom out. Zoom out to 3. And enter. And there we could start seeing a little bit. And we have a little hint here. It kind of gives us some numbers to look at for -4 and 3 on the x-axis and go up to 50 on the y-axis. So I'm going to cheat and just use those numbers. Okay, so I'm going to go over here to Window, and I'm just going to change it to those numbers, right? So I'm going to have instead of -40, let's go -4. Let's clear that. I'm going to put that as -4. And then over here for here it was 3, so I'm going to clear that and just type in 3. And then for my minimum, there wasn't much below the x-axis. I'm going to put maybe -5, just to have a little bit there. And then down to my max, which we said was 50, right? I believe it was 50. Look at that. Yep, 50. So let's make that 50. Change that to a 5. 0. There we go. All right, so now I've matched what was given to us. And yes, definitely. So now we can see it does look like a 4th degree because it does have 3 turns, 1, 2, and 3. Right? Much more reliable than what we had on our initial screen. So we're just going to copy that over. Okay. Copy that right over. This to a different screen. And you can do a little tracing to find out exactly where those roots are. That'd be a good idea. Let's do that, right? So we can see, or at least where those maxes are. There's a relative max right there, right around, yeah, -0.72, 0.71, something like that. Right? And I can go through and do calculate and find out what is that actual maximum. So left bound, enter, right bound, enter. Good guess. Enter. And we can see, yes, -0.72 at 45.89. No, 45.86. There we go. So just as you're graphing it, you can be somewhat accurate if we do all these properly. So that would put us somewhere right around here, and you can write those in. So we have -0.72. Comma 45.86. If we did the same thing for the other, I think this one was pretty clear. It was at 2, 0, so that was pretty straightforward by looking at it. And if we did the other one, the other minimum here, we can practice that. Let's go find this other one. Oh, trace first. Go down here. And we're going to calculate second. There we go. And this one's a minimum, local min. Enter. Left bound. enter, move to the right, enter, and move it to the middle, and enter. All right, we have negative 2.78 and 23.95. We'll use those numbers. So negative, what's that, negative 2.78, so right around here, and 23, let's go right around here. That's negative 2.78 and 23 point, I think it was 95. Right? And then we could draw a nice pretty graph estimating everything else. So here to here, and let's see here, to here. I think it had, it had a double duplicity. There we go. Yep. It's a fourth degree, so both sides are facing up. That checks out. Right? Fourth degree, the endpoints have the same behavior. They either both go up. In this case, they both go up or both go down. That's an even function. And we can take the time to write out that information as well. Right? So we can say, what is the relative min? Right, that's at 23.95. We can say the absolute min is just at 0. And we can say the relative max, and these are just listed in any order, will be 23.95. No. What was it? 45.86. That's the max. Yes. 45.86. There we go. And let's see here. If we wanted to, anything else with characteristics, that could be anything. Characteristics is all the different things. So we can mention the x-intercepts, right? X-intercepts slash zeros, right? Slash zeros and solutions sometimes are called, right? But that's going to be just at 2. And we can say it has a multiplicity of 2 because it bounces off. We could even mention the y-intercept if we wanted to. We found out what that was, but I think that's enough information for now. Yeah, that's pretty good. All right, so lots of information here, right? We had to do a lot of work, but it gives us everything we need to know, right? Especially this part of taking the complex and turning it into a polynomial that we can then graph and figure out the mins and the maxes. Right? So you might notice so far in this class, we're really focused on these mins and maxes, right? That's really our goal. Whereas in Algebra 1, Algebra 2, it was all about the x-intercepts. Where does the ball hit the ground? Where's it leaving from? It's always about what's happening at this ground level. Whereas now, with all these different twists and turns, it's about where are those mins and maxes. All right, so I'm going to keep on going, do a little bit more practice here. So it says factor a polynomial with complex zeros, right? And find all the zeros f of x of this polynomial. So, okay, so we expect, it's saying complex, so if we factor this, we're guaranteed to get some complex answers. Now, here's a little type of factoring technique. There's no GCF, but whenever there's 4 terms, there's a possibility to use a technique called grouping, factor by grouping. So that's what we're going to try here. Grouping means we really just do a GCF for the first 2 terms and a GCF for the second 2 terms and see if they actually have the same term in common. Right? Here's what I mean by that. So if we factor a GCF out of both of those, right, that'd be an x squared, right? Because they both have an x squared in them. And we'll be left with x minus 3. Right? And you'll notice that's what we have here. So the GCF of this right here, we're going to call it 1, and it's also an x minus 3. So look, this polynomial now has a GCF that we can now factor out even further. So what I'm really doing right about now is I'm going to factor x minus 3, since it's in both of them, out. Right? So now I have an x minus 3 that I factored out, And what I'm left with is this x squared and this plus 1. I should put below, plus 1. So in a sense, I factored out a binomial from both of them. That's what the x minus 3 is. And what's left over is the x squared right here and the plus 1 right here. So pretty handy technique to try anytime you have 4 terms. That was back from Algebra 1. All right, and we are trying to find all the zeros, which means where is this equal to 0? So the theorem says that if two numbers multiply together, that this equals 0 or this equals 0. So let's just solve these independently. So x minus 3 equals 0, which we get 3. And then we have x squared plus 1 equals 0. If we solve that, subtract 1 on both sides, we get x squared equals negative 1. And then when we take the square root of both sides, we'll get plus or minus square root of negative 1, which was I. Right? So we got our 3 roots. Right? So we had our third degree polynomial. Fundamental theorem of algebra says we have to have 3 roots, and we got 1, we got 2 with a plus, and 3 with a minus, right? And that corollary just applied right here. We had an odd number, right? We have that odd number here. We go back, let's take a look. Okay, back here, nope, too far. Where did you go? Oh no. Oh, there it is. Corollary, right? So we had an odd function, and we had at least one real root, right? So we ended up this being true and showing that this is true right here. So we had an odd function, we had one real root, and then a pair of imaginary or complex roots. Okay, let's see here. Example 9. So it says we have the complex number z equals 2i, which z is another way of just saying solution. So we know one of the x-intercepts or one of the solutions is 2i, right? And it says find the remaining zeros of f of x and factor over complex numbers. All right. So we actually know that not only 2i is a root, right? We know these come in pairs, so from here we're also going to have negative 2i as a root. Okay. So very important to catch that and see that. So we're going to have, let's see here. Let's go ahead and factor this as much as we can. Once again, let's use the factor by grouping, because we got 4 terms, right? So I'm going to factor the first 2 terms. Notice how we get a 2 that can go into both of those, so that's going to be a GCF. Actually, you know what? There's a factor of 2 for the whole thing. So let's take out a 2 out of the whole thing. That's probably even better. Yeah, let's do that. So we have 5x squared plus 8x plus 20. Yeah, that's better. Okay, and we're going to set this equal to 0 and factor it. Now, notice how we took out that 2, and we set it equals 0. If we just divide both sides by 2, we'll get 0 on the right-hand side, and the 2 will just be gone, because when we divide that by itself, it just equals 1, which is okay. So, in effect, by setting equal to 0, and dividing both sides by 2, I really just have to work with this part that's left inside the parentheses, and I can just ignore the 2. Now, if I was graphing, of course, I would need that 2 there. That would stretch it in a certain direction, vertically, but since I'm not graphing, I don't really need it there. I just need the roots. All right. So now we can look at grouping and look at the first 2, factor a GCF out. Right, so we have, looks like just x squared, right? We can take an x squared out. So we have 2x plus 5. Good. And then we can do the next 2, factor a GCF out of here. So 4 looks like goes in 8 and 20. Keep the colors consistent. So if I take a 4 out, notice how I get 2x. Right? 4 times 2x is 8x. And 4 times 5 gives us 20. Once again, I have a common factor, which I am then going to factor out in front. And I am left with x squared from here and the plus 4 from here. Pretty cool. This is why math is fun. So many cool things. All right. So now we can use the zero product property like we did last time. All right. So we'll have 2x plus 5 is 0. Subtract 5, divide by 2. X equals negative 5 over 2. By the way, that's totally acceptable as far as showing work. You might be used to like the minus 5, solve, divide by 2, solve. However, at this level of math, it's okay to start saying, like, we can all do this in our head a little bit. We can subtract 5 and divide by 2 and say negative 5 over 2 without showing it. It's a very fundamental step that you started doing in 7th grade. And at this point, it's kind of assumed that we can all do that without writing every little step. But if you prefer, you can write it out. That's fine too. We'll solve this one equal to 0. So we'll get subtract 4. X squared equals negative 4. Square root both sides. So we have x equals, don't forget, plus or minus 2 for the 4. Square root of 4 is 2. Square root of negative 1 is the I. So we have our complete set of zeros, right? It gave us 2i. We now know, of course, and we already knew at the beginning with that there's going to be also negative 2i. And then we found the third one, which was negative 5 over 2. So we just list those in braces. Negative 5 over 2, and 2i, and negative 2i. All right, this is going pretty well. Let's see here, number 10. Okay, so it gives us 1. So very similar, only it gives us a real answer, a real solution, as opposed to here it gave us a imaginary. But notice how this one said x equals is 0. This one said z equals. They're equivalent. They're just different ways of saying the same thing. As I mentioned, z is a different shorthand for saying solution. So we need to figure this out here. What can we do here? So we need to know what polynomial. Like, we need to factor out an x, a factor of x here, and this is a 4 term. So my first instinct here is to do what we did last time, right? Let's try grouping, and let's look at the first 2 terms and the second 2 terms. So let's try to factor that, and we get x squared is x minus 1. And then over here, my GCF is only 1, really. Nothing goes into 7 and 5. Okay, maybe negative 1, but that'll give me a 7x and a minus 5. And unfortunately, the grouping didn't work because these two did not come out to be the same. So, in that case, we're going to have to get fancy. Since that didn't come out to be the same, grouping failed. So we're going to have to do some long division or synthetic division. So you might remember from Algebra 2 that we can figure out what the remaining factor is just by doing some long division, but we're doing it with polynomials. I'm going to leave myself a little room here. Nope, that's the wrong one. Nope. Let's do erase. There we go. So leave a little bit of room. So we're going to do some long division here. Okay, and one of my factors is x minus 1. Right, and I'm going to divide that into my polynomial to see what's left over. Plus 5. There we go. All right, so we have to say what times x gives us 3x squared, right? So we'll get 3x cubed, sorry. We'll get 3x squared. So 3x squared times x gives me this 3x cubed. And 3x squared times negative 1 gives me minus 3x squared. And just like long division, we draw a line. And you have to subtract. Very careful here. So it's really negative x squared minus a negative 3x squared. So minus a negative is positive. So we have really 3 minus 1, which is 2. X squared. And we bring down our negative 7x and just repeat this process. So what times x is 2x squared? We put 2x. So we have 2x squared minus 2x. All right. And once again, negative 7x minus a negative 2x is going to be plus. So we have negative 7 plus 2 is negative 5. Bring down the 5 and repeat one more time. So x times what is negative 5x? We have negative 5. And we get negative 5x and positive 5, which is good, because subtract those, we get 0, which means it went in evenly. All right. So that's a little review with long division. Now, for some of you might have thought about, well, what about synthetic division? That's a faster version of this. So let's look at synthetic version. So I'm going to put a big OR. Right, synthetic division. We're going to have 1 in front. And you might need to review this, which means look it up on your own. And remind yourself how to do this. This is a cool little strategy. So 1 is my 0 here, so I just put 1 instead of minus 1, because this uses factors. This is actually using the solution, which we know is 1. And we put the same coefficients, 3, negative 1, negative 7, and 5. 3, negative 1, negative 7, and 5. Right? And you start off with bringing down this 3. And you just multiply and add. So 1 times 3 is 3. 3 minus 1 is 2. 1 times 2 is 2. Go ahead and add 5. And 1 times negative 5, 5, add is 0. Notice how we got the same 3, 2, negative 5. 3, 2, negative 5. So we get the same solution, but boy, synthetic division is a lot faster, right? And you don't have to worry about minusing and subtracting a negative over and over and being very careful. This is a much cleaner way of doing it, and they're equivalent. So synthetic division and long division with polynomials. Okay. All right. So after all that work, what did that tell us? What did we actually gain from all this? All right, so we already knew one of the factors is x minus 1. Okay, so we know that's the truth. Right. The other thing we gained by either method, right, is that the other factor is 3x, right, plus 3x squared. Get that correct. 3x squared. And we have plus 2x. And we have minus 5. Right? And now we can attempt to actually solve this, right? We can actually, remember the whole thing was to find the zeros. This is equal to 0. We can actually attempt to solve this. So we already know we can try to factor this. You can use quadratic formula. I always like to try to do factoring first, right? Just to see if that works. So we can say what multiplies to 3x squared? It'll be 3x and x. If this doesn't work, we can just do quadratic formula. And I need to multiply it to negative 5, right? So I have, let me try about 1 and negative 5. Okay? And I just have to make sure the outsides and insides gives us positive 2. So I have, it's like negative 15. Oh, no, that's way off. Negative 15 on the outside. And we have plus 1, that's negative 14. So that's not going to be it. Let's go back. Let's just switch these. Let's do, how about 5 and 1? Let's do that plus and that minus. Just a good guess. So here we have 3, negative 3. Oh yeah, and then plus 5. So negative 3 plus 5 does give us positive 2x. So that is the correct factorization of this. Now, if you just want to do quadratic formula, you get the same thing. So that's okay too. So I have my 3 roots that all multiply to 0. Whoopsie. All multiply to 0 here. All right, so I'm going to do, kind of squeezed here. So I'm going to do x minus 1 equals 0 from here. So that just means, and we already knew this, right? It gave us that one. And then I'm going to have 3x plus 5 equals 0. So from here, I'll get x equals negative 5/3. Okay. And then from here, I also get, looks like x plus 1. X minus 1 equals 0, so we get there. All right. So here's the full factorization, right? And here are the three different zeros. It's a 3rd degree. We do have 3 roots, so we are good to go. So we can write this as, let's say, negative 5/3, and 1, and negative 1. Now, it is a good idea to write out as opposed to plus or minus 1, because when we're expecting 3 different roots, it's nice in our answer to actually see 3 different numbers. So you could write plus or minus, and you could say 1, oh, then 2 and 3, but it's a little bit neater and cleaner just to write out all 3 of them so that that matches up. Okay, so that was a good exercise in Algebra 2, right? Now, many of the AP questions will not involve this much Algebra 2, right? They might involve a little bit, though. So it's good to brush up on all of it and realize how much you've learned up to this point, and to practice these skills so that if you do need them, you remember how to do them, right? So, but don't worry that you will not have a bunch of AP pre-calculus questions that make you do problem after problem with this much different calculations. But any one of these practice problems might come in handy, right? It might be useful to remember how to, let's say, factor by grouping, right? That might be useful at some point. So we have to keep practicing these, different techniques from all the classes before this one, just to make sure we still remember it and we can use it anytime it might be needed. All right, good job, everybody.